From the 22 News Plus studio, this is 22 News in Focus with Patrick Berry.
Hello, everyone, and welcome to today's edition of InFocus. I'm your host, Patrick Berry. We are here in the 22 News Plus studios. We're having a fascinating conversation today to talk about our climate. And unless you've been living under a rock, you should know that our climate has been changing. We'll talk about climate versus weather, some of the ways scientists are learning that our climate is changing. But I'm very fortunate to be joined across the desk today by Dr. Julie Brigham-Grette. She is a UMass Professor of Earth Sciences, and she's one of the department heads up there. Julie, thank you so very much for joining me today. I can't wait to pick your brain.
Glad to be here.
So I do want to start off with talking a little bit about you. How does one become a climate scientist?
It's really interesting. I found that I really liked, I discovered the earth sciences when I was a freshman in college.
Okay.
I was planning to be a forestry major, but
Okay.
I discovered the earth sciences.
All related.
All related. And I also discovered that I just love field work, like being outside and camping and that type of thing. So that kind of family field trips and camping trips really rubbed off into a career that's taking me all around the Arctic for most of my career.
And that in and of itself is worth a full InFocus episode just to talk about your travels and what you've experienced. But you really focus on climate change. That's sort of your specialty, correct?
That's right. So I've been fascinated with past climate change, just like studying the history of the planet over the last 3-4 million years. How did we go from a forested Arctic or even a tropical Arctic? If we go back millions of years, it was tropical. Then we went to forested Arctic, and now we have this Arctic that's cold and has interglacial events. And I was fascinated by that. Then I thought about the relevance of what I do and how does it impact society. And as we continue to warm the planet, I started to see how my information about how quickly we're changing the planet and what we're setting in place really matters. And people need to understand the urgency of getting off fossil fuels.
So your research has proven beyond a shadow of a doubt that humans have impacted the climate.
Absolutely. Absolutely. We have, there's some events we can talk about that happened 55 million years ago when there was a rapid release of methane and CO2 into the atmosphere from volcanic eruptions and other things. And that caused a massive extinction of the surface oceans. It took 20,000 years to happen, but then it took the Earth 200,000 years to recover from that.
Wow.
Now, what we're doing to the planet now is 10 times faster than that event. So we are acidifying the ocean. We're changing the atmosphere at rates we've never seen before as Earth scientists.
So how do you prove that? How do you know what happened, 100,000 years ago, 200,000, a million years ago? And how can you say that what's happening now is so much worse than what happened previously?
So we're lucky that we have this particular event that happened about 55 million years ago is really well recorded in the oceans. So in the bottom of the ocean, there's layers of sediment, just like layers on a cake, that accumulate over decades to centuries and millennia. And in those sediments are fossils that tell us about the chemistry of the ocean, the temperature of the ocean, and what was alive, what wasn't by absence. And so we can tell the age of that material relatively well. So we actually can map the change in time and then come up with these estimates that it took about 20,000 years for the world temperature to raise 5 or 6 degrees. At the same time, we acidified the oceans in that time period. And then, because there weren't any humans around 55 million years ago, of course, naturally, the Earth system buffered itself and the oceans returned to normal and life came back into the surface oceans. But it took 200,000 years for that to happen. So this is why I think as Earth scientists, we need to tell these stories about these events that we can see. We're not joking. This is
This
real.
isn't fake news.
This isn't fake news. That what we're doing to the planet now on this is unbelievable. What we've done in just 100, 150 years.
So there is a common misperception of the climate versus the weather.
Right.
Okay, so let's start with weather. So explain to me, what is weather?
So weather literally is what you see out the window. It's right, it happens every day. It's radical. We can predict it. Brian Lapis can predict it within a matter of days. And sometimes it doesn't quite follow the pattern, but we got to have a pretty reasonable idea.
Fairly close, yeah.
But weather is the day-to-day changes. Climate is actually defined scientifically as the average of 30 years.
Okay.
So if you take 30 years of data, and it's a moving window, right? Next year we'll move the window up a year. So it's the average climate is the average weather over 30 years. So you can take Chicopee or Amherst or someplace in Brazil and come up with a average temperature for that area and average it over 30 years. And so what we're seeing is a shift in that 30-year average.
So when we see in the summertime heat waves here in New England or Montana, North Dakota, where temperatures get really, really hot, Canada, Canadian West, or conversely in the winter, like this past winter, we've seen Florida falling iguanas.
Right.
We never saw that before. We never saw that type of weather before. Is that a result of our climate changing?
Yes, it is.
Or is that just those
so the climate
outliers?
The climate is clearly warming on the whole planet, and so what is happening is as predicted by some climate models is we're getting more erratic climate, more extremes.
Okay,
and that's happening more frequently. So why is that happening more frequently? Part of it is the waviness in the jet stream is getting more erratic. And larger swings,
ebbs and flows.
So like the recent weather, we've had these extreme cold events reaching all the way to Florida. That's because those are like outbreaks of the jet stream coming way south. Whereas at the same time, if you look elsewhere on the globe, you've got warm temperatures getting way north.
Right.
And so just recently we've had weather where it's extremely cold here, but it's actually anomalously warm in the high latitudes because these outbreaks of the jet stream. And scientists are still making observations to really firm that up. But generally speaking, it's becoming much more frequent. And it's the same with, I would say, with hurricanes. Hurricanes aren't necessarily getting more frequent, but they're getting more intense.
Right.
So those are the kinds of shifts that we see.
We are up on our first commercial break. When we come back, we're going to dig in a little bit more and a little closer to our climate and how it's been changing. So stay with us. We're back in just a moment.
This is 22 News in Focus with Patrick Berry. This is 22 News in Focus with Patrick Berry.
Welcome back, everyone, to today's edition of InFocus. I'm your host, Patrick Berry. Sitting across the desk from me, I'm honored to be joined by Dr. Julie Brigham-Grette. Thank you so very much for coming in. She is a professor of earth sciences, and primarily studying the climate across the globe. We're going to get into a number of slides now that sort of visually explain what's going on. Let's get right into it, Julie. The Arctic is in disarray. What does that mean?
So, this slide came out from Climate Analyzer, which is a website which is out of the University of Maine. And it shows the anomalous temperature difference between the high latitudes and, of course, where we are here in the East Coast of the United States. And, of course, because of the change in the waviness of the jet stream, it causes these outbreaks of really cold air coming way south. And at the same time, that is balanced by warm air going way north. So here you see Greenland and parts of Arctic Canada are actually 30 degrees warmer than normal, whereas here we are at 30 degrees colder than normal because of that waviness in the jet stream.
Over what period of time? Is this like we talk climate is a 30-year average? Or is this last winter?
This is actually a snapshot of just last week.
Oh, wow. Okay.
And so that's going to change from week to week, of course. But another thing we notice about the waviness in the jet stream is that because it's wavy, it's like a meandering river in a sense. It takes longer for these systems to move out. So this is why we're getting more intense rainfall, because the waviness is causing these blocking systems to set up, and then those extreme weather events last longer in any one place. So if we come back and look at so here, this figure here, this is out of NOAA. On the left-hand side is kind of normal flow of the jet stream with our normal weather coming from the west, going to the east. And it's more or less kind of a straight river system. That's what we would expect.
Consistently predictable weather.
Right. And on the right-hand side is, in fact, this increase in waviness in the jet stream, where we have much colder air coming much farther south and warmer air going north. And scientists are still debating why this is happening, why it's becoming more frequent. But one idea that I think is a nice simple explanation is that as the whole world warms up, the Arctic is actually warming faster, and therefore the gradient from cold to warm, from the tropics to the polar regions, is getting flatter. So the gradient is flatter. And like any river system, on a flatter landscape, you get a more meandering river, just like our Connecticut River.
Okay.
So the idea is that it's these outbreaks may be because of global warming and because of the decrease in gradient from the tropics to the polar region.
And looking at the image on the right, those peaks and troughs move. So it's like it's the cold trough dips down to the Carolinas here on the East Coast near in Florida, but that'll move.
It will move, but it moves more slowly.
Okay.
So we're used to weather systems coming in and going out rather quickly, maybe a storm in a day.
Right.
What this does is it sets up a bit longer period of time.
Interesting.
So that's becoming more frequent.
Explain to me this picture. I mean, I think I could kind of interpret it, the ice receding, but where is Kongsfjord?
So Kongsfjord is on the island of Svalbard, and Svalbard is about 400 kilometers north of northern Norway. So it's up at around 80 degrees north and 79 degrees north. And what we were doing here, studying with funding from the National Geographic, was to look at the influence of the warm North Atlantic water coming up along the coast of Norway and then all the way to Svalbard, and then actually causing massive retreat of the glaciers there.
So as we think about here in the eastern seaboard of the United States, the Gulf Stream comes up along Florida, Georgia, the Carolinas, and then heads out. But because that water's much warmer, you think about it, it goes out, Nova Scotia, Greenland, Iceland, up to Norway.
To Svalbard, right.
So this is really a result of the
warming planet. And you're seeing that what's happening is that warm North Atlantic water is getting up into those fjords more than it had before. And what was interesting with this, I had been up here many, many years, and in 2005 was the last time that this fjord froze over in the wintertime. It used to be that prior to that, for decades and decades, people could snowmobile or ski across this fjord in the winter, and now it doesn't freeze over. It's open the year
since
round.
2005.
Yes. And so on the left, upper left, is a picture that we took from the airplane in 2011. And then the one on the right is 2021. And you can see that there's been this massive retreat of the ice
in 10 years.
In just 10 years. And so this is really quick retreat of the ice. And we're able to then, with some simple instruments, measure the water temperature that's reaching the face of the ice and causing not only the calving and the breaking off of the ice, but also just melting it back.
Let's talk a little bit about measurements.
Mm-hmm. So This thermometer on the left is from a group that one of my favorite groups called the Climate Action Tracker. They track the carbon dioxide and fossil fuel emissions from all the different countries and the promises they make to the Intergovernmental Panel on Climate Change for the UN. And what this thermometer shows you is essentially taking the temperature of the planet, like putting a thermometer under your tongue to check your body temperature. This is a thermometer showing the temperature of the planet. And in the green there, you see a line across there that says pre-industrial average. So we call that zero. So if we go back to, say, 1870 or something, that we call that our zero state. And so what we're looking at is the change in the climate of the entire world since that time. And we know from studying Earth systems that if you warm the planet just even a small amount, you're going to start to get more extremes in weather and all kinds of changes happening. And so what the Intergovernmental Panel on Climate Change and what the so-called Paris Agreement was to try to limit the warming of the planet to 1.5 degrees. And we're kind of there now. Okay. We've reached that point, and it's not like it's not like we're shattering some kind of threshold. It's just that we're going to see much more rapid response of different parts of the planet system because we're getting warmer. I even have family members who have said to me, Julie, 1.5 degrees is nothing. Right? Doesn't sound like much, but I'd like to make the analogy that, we have a body temperature that we are used to. We know when we're healthy. And if your temperature goes up 1 degree or 1.5 degrees, you notice it, and you might actually have to go to the doctor.
Right.
If it goes up 3 degrees, you really have to go to the doctor. And think of it in the other way. If your body temperature goes below 95, you're actually approaching hypothermia.
Wow.
People don't think about that. So think about the planet in the same way. If you're averaging tropical temperatures to Arctic temperatures all over the globe, 1.5 degrees is a lot of temperature increase. And so what I do in my work is looking at past climate change. Okay. Is I'm studying glacial, interglacial changes. And we come up with averages to give that 1.5 degrees of perspective.
Perfect. We are up on our second commercial break. When we come back, I want to get into, what is it, paleoclimate is the phrase?
Yes.
We're going to talk about paleoclimate in just a moment. Stay with us.
This is 22 News in Focus with Patrick Berry. This is 22 News in Focus with Patrick Berry.
Welcome back, everyone, to today's In Focus. Today, we're talking about climate change, and I'm very honored and fortunate to be joined across the desk by Julie Brigham-Grette. She is a PhD from UMass Amherst, and her specialty is climate. So thank you so very much for joining me. Folks, I don't know about you, my mind is completely blown with the information that you've provided me already. And I want to jump right to this next slide because this is extremely eye-opening. But Julie, dumb this down for me and everyone else.
Okay. Yes. So this is a diagram that shows on the top wiggles.
Let's see if my mouse works here.
Yeah.
Okay.
That top one there is different segments of time with on the far right shows you the projections of carbon dioxide in the atmosphere from where we are today at about 440 ppm. And then the future projections if we, in the worst case, don't do anything about fossil fuels.
So at the very top here, where I hope folks can see the cursor, these are the different periods of time of planet Earth.
Yes. So this is going back. These are snapshots of time. On the far left is this time in about 55 million years ago in the Eocene when we had really extreme warm times. And then you see generally the next panel is the last 5 million years. So that takes us in to look at the Pliocene. The atmosphere we have today is actually a Pliocene temperature, Pliocene atmosphere. And then in the middle panel are the glacial interglacial changes with climate warming and cooling because of changes in the Earth's orbit around the sun and the tilt of the planet, of course. And then the next panel is kind of coming out of this last ice age and then going into the future.
Okay.
So the point of this diagram is that if you look at where we're at 400, if you can put your cursor on around 400 ppm, go up there.
400 ppm.
Yeah, there it is, and take it across. We're now at 420 since this diagram was made, and if you go all the way over to the 3 million years ago in the second to the left panel.
Where'd my cursor go? Oh, there it is.
Keep going left. Okay, right there. You see that's when the planet, from our best estimates, had CO2 pretty much about where we're at, around 400 to 420 parts per million. So what was the world like? We don't think there was a Greenland ice sheet, so it didn't exist yet. Lots of the high latitudes, we had ice in Antarctica, but we didn't have any ice in the higher latitudes, or not much. And sea level was somewhere in the range of about 20 meters above present, or about 60 feet higher
than where we currently are. So Cape Cod would be underwater.
Cape Cod wouldn't have existed.
Yeah.
Most of all Florida is underwater. The eastern seaboard, right up to the Appalachians, would have been underwater at that time.
Right.
And we have the geologic evidence of that. So people like me working in other parts of the world, we can see how high sea level was during that time. So what we're doing today to the planet's temperature is we're driving it in the direction of where we were in the Pliocene.
Okay.
Now, that doesn't happen overnight. So at present, if we don't do anything differently than we are, then the Greenland ice sheet will be mostly melted in about 1,000 years. Okay. If you're a politician, that sounds way out there. And
right.
So they don't care about that. But the problem is sea level is rising. And so we're seeing more coastal erosion. Plum Island, if you haven't been up there lately, that's on our eastern seaboard, is eroding quite quickly. You can look at Florida. We have what's called sunny weather flooding, where we have a king tide because of the moon. Sea level is now rising up into parking lots and into people's backyards.
We're seeing that along the eastern Massachusetts shoreline too.
Exactly.
And Connecticut shoreline, Rhode Island.
Exactly. Yeah. So sea level is accelerating. If you go back 100 years ago, our best estimate that it was rising. And again, this sounds small, but it's 1 or 2 millimeters a year. But now we're up to over 4 millimeters per year.
Wow.
And so it's accelerated quite a bit. And again, that doesn't sound like much, but if you live in, for example, the Mississippi Delta, where you have naturally it's sinking, they're extracting groundwater for the city in New Orleans, and that's causing more sinking of the ground. So you've got sea level rise accelerating on an area that's already sinking, and that's happening in the Nile Delta, deltas around the world, Bangladesh, for example.
Wow.
So sea level is coming up, and it's going to cause more and more erosion.
And I don't mean to end it there, but that's scary. But unfortunately, we are out of time. But Julie, I cannot thank you enough for really explaining climate change to all of us. Thank you so very much. Good seeing you.
Thank you for the opportunity.
This is 22 News in Focus with Patrick Berry.